Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we gave an introduction of Gauss's law. Today we will explain it. So my topic is Gauss's law of electrostatics. Sometimes is also referred as Gauss's theorem. Last time we said that we can find electric field surrounding any charge due to Coulomb's law. Using Coulomb's law, sometimes calculation may be complicated. Now we have alternative method to Coulomb's law for finding electric field surrounding a charge, that is Gauss's law, right? And we said that Gauss's law is valid in all situations, but we use it in only certain situations where there is some sort of symmetry. There is involvement of symmetry, right? And in those situations, calculation using Gauss's law is easier compared to Coulomb's law. Today, let us give the statement of Gauss's law. Statement goes like this. Suppose we have charges. Let it be Q1, Q2, Q3, Q4. We can have any number. Some of these charges can be positive, some may be negative, right? Or all may be positive, all may be negative. There is no restriction on that, right? Now, if I select some point surrounding these charges, and these charges can have any number. Now, if I select a point, for example, this point P. Now, the electric field at this point, EP, electric field at point P is EP. That electric field from superposition principle will be sum of E1, electric field due to Q1, E2 due to Q2, E3, E4. That means if I have 4 charges, this EP will be vector sum of E1, E2 plus E3 plus E4. And I can have any number of charges. Accordingly, there will be terms in this sum. Now, if I have to find this electric field at point P, Gauss's law says, what do you do to find that? Construct a closed surface, right? Now I construct a closed surface. Now that closed surface will pass through this point. And that closed surface can have any shape. Let this be my closed surface, right? So this was my point P. Now this is my closed surface. Now this closed surface we call Gaussian surface, right? Gaussian surface. Then Gauss's law says what you do, you calculate the net electric flux through the surface. Now let phi subscript E be net electric flux through the Gaussian surface, right? Now from definition of the electric flux, we've already discussed that. Then my electric flux will be integral E dot dA closed, right? This E is electric field over the Gaussian surface. And remember, when I calculate the electric flux, what I do, I divide this closed surface into infinite small parts dA, represent each piece by a vector, and that area vector at each point is taken as outward normal. For example, here dA will be like this, here dA will be like this, here dA will be like this. So at every piece of area vector is to be taken as outward normal, and it is to be dotted with the electric field there. Electric field here will be dotted with this dA, electric field here will be dotted with this dA, and so on. Then we add these dot products over the whole closed surface to find this electric flux. Now E here is the net electric field as a location of the area element. That's the net field EP, right? So EP is my E in the integral. So let me write, or you can understand, EP is E. You don't need to change EP symbol to E. I was just giving examples if I have some point, right? Now Gauss's law says that when you calculate this net electric flux through the surface, then your electric flux through your Gaussian surface will be equal to Q by epsilon naught, where Q is net charge inside the Gaussian surface. And epsilon naught, you know, it is the permittivity of free space. And you know this is valid in vacuum. So this is valid in vacuum. So this thing you need to remember. This equation is the statement of Gauss's law. Gauss's law or theorem for electrostatics. I repeat the theorem. I said, suppose we have charges Q1, Q2, Q3, Q4, right? I can have n number of charges, right? I have shown only 4. Now, all these charges can be positive. They can be all negative. Some can be positive, some may be negative. For example, let this be positive, right? Let this charge be negative. Let this be negative, right? Let this be positive. I'm specifying. So I'm taking Q1 positive, Q2 negative, Q3 negative, Q4 positive. They can be all positive, they can be all negative, they can be partly positive, some negative. There is no restriction on that. So now I again repeat the statement. I have some point charges. Now I select some point P in their neighborhood. At that point, there will be electric field. That electric field will be vector sum of the individual fields from superposition principle. Now, in order to find that electric field using Gauss's law of electrostatics, what we do, we construct a closed surface called Gaussian surface. Now, that Gaussian surface, that closed surface can have any shape, right? I have constructed this Gaussian surface this way, enclosing Q1, Q2, and Q3. Now, my Gaussian surface may enclose all the charges. It may enclose no charge. It may enclose only positive charges. It may enclose only negative charges. It may enclose some positive charges and negative charges. There is no restriction on that. Then I calculate net electric flux through the Gaussian surface using the definition of electric flux. Now, once I calculate the net electric flux through my Gaussian surface, then Gauss's law says that electric flux through this Gaussian surface, closed surface, is always equal to Q by epsilon naught, where Q is the net charge inside my Gaussian surface. Remember this, Q is the net charge inside the Gaussian surface. For example, here, what's my Q? I have three charges inside the Gaussian surface, Q1, Q2, Q3. Q1 is positive, Q2 and Q3 are negative. Therefore, my Q is Q1 minus Q2 minus Q3. This is the meaning of net charge inside the Gaussian surface. Q1 minus Q2 minus Q3, right? So this is the statement. When we use Gauss's law to find the electric field due to some charge, selection of Gaussian surface is central to the calculation of the electric field. Our priority is to select a Gaussian surface in such a way so that this E dot dA reduces to EDA. E dot dA reduces to EDA. How is that possible? If electric field and area vector are everywhere parallel, angle between them is 0, cos 0 is 1, then this E dot dA will reduce to EDA. So I have to select my Gaussian surface in such a way that this dot product reduces to EDA. Another thing, then I try to choose the Gaussian surface so that electric field over the Gaussian surface is constant and this electric field can be extracted outside this integral, right? So first thing, E dot dA should reduce to EDA, then electric field over the Gaussian surface should be constant if possible, so that E can be taken outside the integral. Then this integral becomes just E times closed integral dA. Then this thing is simply what? Surface area of my Gaussian surface. And my Gaussian surface should be some regular surface so that its surface area is surface area is calculatable. we can calculate that if it is a regular surface, right? Now, again, I want to emphasize this Gaussian. So, this Gauss's law of electrostatics or Gauss's theorem is actually saying in a way that the net electric flux through Gaussian surface is proportional to the net charge inside the Gaussian surface. That means if net electric flux through my Gaussian surface is positive, then it must contain a net positive charge inside it. If net electric flux through my Gaussian surface is negative, it must contain inside a negative charge. And if it is zero, the net charge inside it must be zero. For example, if I draw the lines of force for electric dipole, let this be plus Q and this minus Q. You know, electric dipole is a configuration of 2-point charges of equal magnitude but opposite sign. Then the pattern of lines of force surrounding these charges will be like this. You know, electric lines of force leave positive charge and end at negative charge. So it will be like this, right? It's like this. So this is the approximate electric field surrounding an electric dipole. Now I draw 3 or 4 Gaussian surface. Let this be my one closed surface, S1. Then I construct another Gaussian surface. Let this be S2. Now this S1, this S2, let this be S3, another closed surface. Let this be S4. Now we already know from the definition of electric flux, when we calculate electric flux through some closure surface, we know that leaving flux is positive, entering flux is negative. According to this definition, flux for electric flux for S1 is positive. Why? Because everywhere flux is leaving the surface. Right? So electric flux for S1 is positive. What about S2? For S2, everywhere electric flux is entering the surface. So flux for S2 is negative. What about S3? Flux for S3 is 0. Why? Because leaving flux is equal entering flux. 4 lines are entering S3 and 4 are leaving. So net flux through the surface is 0. What about S4? Same is the situation with S4. Phi E for S4 is 0, right? Because these lines are within S4, so they will not contribute to the flux. These lines will give positive flux. These 3 lines will give negative flux. So net flux through S4 must be 0. This is from the definition of electric flux. Now, if we see Gauss's law, same is the prediction of Gauss's law. See S1 contains net positive charge inside it. So flux, though it must be positive because flux is proportional to the charge. Electric flux is Q by epsilon naught. Flux for S2 must be negative because it contains a negative charge inside it. Flux for S3 must be zero because it contains no charge inside it. And same flux for S4 must be zero because it contains two charges, Q and minus Q, but net charge inside S4 is zero, so flux must be zero, right? So this was an illustration of Gauss's law. Now, what we do, we here enter into the second unit second of your syllabus. It starts with applications of Gauss's law, right? We do one application. First application is electric field due to a point charge you want to calculate the electric field due to a point charge using Gauss's law. You already know from Coulomb's law, you calculated that Coulomb's law says that if I have some charge plus Q and I select some point P r distance from it, then electric field at point P to this point charge will be 1 by 4 pi epsilon naught Q by r square. We will see that Gauss's law gives the same result, right? Now suppose I have a positive point charge Q. Now we know the pattern of electric lines of force surrounding this charge. Now electric field everywhere is outward radially. Now in using Gauss's law, first thing is to construct a Gaussian surface. Now we construct a Gaussian surface spherical in shape and centered on the charge with radius r. This is my spherical Gaussian surface centered on the charge Q, centered on the charge Q let me fix this. Centered on the charge Q with this is charge Q with radius r, right? Now why we have selected this Gaussian surface? Because when it is centered on the charge, at every portion of the Gaussian surface electric field will be constant. Another thing, electric field everywhere is radially outward, so area vector and electric field will be everywhere parallel. I show it at one place. Here area vector will be this way, dA, and electric field is also outward. So angle between theta between electric field and area vector is 0 degree. Same is true everywhere, right? Now applying Gauss's law. Applying Gauss's law. Says net electric flux through the Gaussian surface is Q by epsilon naught. Q is net charge inside the Gaussian surface. Now, what is net charge inside my Gaussian surface? That is Q. So Q is Q, right? Now, what is my electric flux? First, it will become EdA cos 0, because everywhere electric field and area vector are parallel. Then it will become E closed integral dA is equal to Q by epsilon naught, right? The electric field everywhere is constant. Each portion of the Gaussian surface is equidistant from the charge. So electric field is constant. What is this? This is simply surface area of the Gaussian surface. Surface area of the Gaussian surface, which is simply 4 pi r square, because it is sphere with radius r, right? So what I get, E 4 pi r square is Q by epsilon naught. So my E is 1 by 4 pi epsilon naught Q by r square. This is my result. So I have calculated the electric field due to a point charge Q r distance from it, because electric field E in Gauss's law is electric field at the location of the Gaussian surface, which is r distance from the charge. Now see, same result as you obtain from Coulomb's law. So electric field due to a point charge Q, r distance from the charge is 1 by 4 pi epsilon naught Q by r square. This was one application of Gauss's law. I will give you some homework. You must do your homework. The first question, these are very easy questions, do them. What is the magnitude? What is the magnitude of a point charge of a point charge chosen so that the electric field (75 centimeter away) has the magnitude 2.3 Newton per Coulomb. I repeat the question. What is the magnitude of a point charge chosen so that the electric field 75 centimeter away has the magnitude 2.3 Newton per Coulomb? Another question, question number 2. An electron is accelerated eastward at 1.84 into 10 raised power 9 meter per second square by an electric field. An electric field. Determine the magnitude and direction of the electric field. I repeat the question. An electron is accelerated eastward at 1.84 into 10 raised to 9 meter per second square by an electric field. Determine the magnitude and direction of the electric field. So this is all for today. Thank you. Do your homework. God bless you. Assalamu alaikum.